the next topic, functions of multiple variables. Okay, so let me first review the picture that I showed you how to outline the course based on the subject matter and the different kind of functions. Yeah. Okay. Okay. So, all right. So I just made a picture that looks prettier than before. So, okay. So two dimensions. The dimensions of the main one, 2, and then on dimension 3. Okay. And then also dimension 3 as well here. So this is calculus 1. Calculus 1 is this. Okay, let's try again. No. Okay, so the interaction is the interactive part of the. So this is paint, and it just doesn't work well with the. Doesn't want to play well with the tablet. Okay, anyway, so this is calculus 1. Okay, and okay, and then now we have made this step in this direction. Okay, towards parametric curves. So these are parametric curves. Parametric curves, even though we did not stick with dimension 2. So parametric curves, and then the dimension is valid. All we have developed is totally applicable to all dimensions up from that. So it means that this is what we have been doing is maybe like this. Okay, so on and on in dimensions. So if you go to dimension 3, then for example, parametric curves on the plane, that is dimension 2. So the output space is one dimensional. So you can have a circle, ellipse, any kind of spiral, but you go to dimension 3, and then we had pretty much the helix that we had. That was the only example that we really given consideration enough attention. So okay, and now we are moving in this direction. Okay, so the point is, I want to make that point clear that we do no longer go diagonally. Okay, so whatever we will be using right now will be entirely coming from calculus 1 and not from parametric curves. They do interact with each other, but they neither this does not rely on that, and neither vice versa. Okay, so it is just the way it works. So we based remember the parametric curves in dimension 2. What is a parametric curve? It is two numerical functions. Okay, so if you like, I could. How about like this? 2 arrows indicating that once you get 2 curves like that taken together, they create a parametric curve on the plane. If you take 3, you have a curve in space. Okay, so we do not. Then it's like that game kids play on you draw squares on asphalt, and then you jump or hop on one like this. So that's what we did, and then but you're not supposed to jump diagonal. Okay, so we are coming all the way back, and now we jump to the right. Okay, we could have started this way, and once again, since there is no relation between, or the dependence between them, there is no limitation on in that matter. We could have started on the right and then proceeded to parametric curves. But parametric curves are easy because the whole calculus is just up to the point where we started doing the curvature. Everything resembles very much the behavior of the all calculus 1. So derivatives, all the rules of the derivative, including even the chain rule, integration, everything. You just do it component-wise and you're fine. Okay, so and then this will be slightly more complicated. As you can see, if you ask, so two curves, right? Two numerical functions give you parametric curves. How many functions will give you a surface?
I guess if you're going to describe it the same way, it would take infinitely many.
Infinitely many, right? So either you slice it that way, this way, doesn't matter. Infinitely many curves. More likely you go from here to there because you take this and you slice, not the way it is shown, but rather through the vertical planes. If you slice them, you'll get infinitely many of these. Okay, so that sort of suggests that there's more complexity than that. So calculus 1, we had curves here, but not all. Why not? Because the vertical line test. The vertical line test does not allow us to have a circle, for example. Okay, so that's why, well, one reason why we study parametric curves. So apart from all the motion and physics. Okay, similar thing is going to happen here. So we are going to be we'll be concentrating on this. And we'll have all kinds of surfaces, but once again, not all. And why not? The reason is the same, the vertical line test. Surface, try to, once again, imagine a vertical line, so it's surface standing on this plane, and then if you draw a vertical line parallel to the z-axis, and then if there are two intersections, then it's not a function of two variables. Okay, so for example, if you want to study a simple thing as a sphere, you have to go way up in the dimensions. Okay, because it fails the vertical line test. Okay, so that's roughly the plan, and then once we're done with this, we will do this trick. So parametric curves, the knowledge of parametric curves and the knowledge of functions of two variables will give us the next step, the next stage, closer to the end. But before we proceed, I actually wanna do something to. I just realized I had some little bit of unfinished business last time. It's about curvatures, and the problem was I felt I gave you the impression that maybe it is all dependent on the curves that we choose, the parameterization that we choose. And the parameterization, this one, doesn't have the right circle. Yeah. Okay. So, that's number one. Circle. I guess it just didn't. I'm afraid it just didn't save. Okay, so that's still the helix. We worked that out. Oh, here it is. Okay, the point being that we have done all the computations of the curvature with a very little various parameterizations, but they all work constant speed. So, okay, if the speed is constant, that's easy to reparameterize it. We did it for the circle and for the ellipse. Not for the ellipse, but for the circle. So this is a circle, but it is not parameterized with a constant speed, but rather a variable speed. So if you look at what's happening here, so I did nothing to these columns. Okay, so it's all applicable to any curve, and in particular all curves that parameterized in any other way. And as you can see, what's happening here is, well, don't even have to indicate what show what the formula is. Look at how it is changing in a non-uniform fashion. So it's first it progresses by 0.21, then by 0.25, then 2.9, and so on. So in other words, it is spitting out as far as the step of the parameter t is concerned. And just to demonstrate that it still works out, the formula, the way we computed the curvature through the unit tangent vector and its derivative, it all works out. As you can see, the circle still has, at least at the limit, produces the curvature of 1. Okay, so just to show you, and the second point that I was making is that I felt that may have given you the impression that this wouldn't work with, that is specific to this curve. You can plug in any data here, you can plug in and it will produce the result. It's just harder to compare it with anything specific. If it's a circle, we know what it behaves like, we know what its radius is, and therefore the curve. Okay, so, all right, so this is, we are going to discuss this. Well, actually, I want to leave you with one question about curvatures, and that is so we have demonstrated, the discussion at the very end of yesterday was about the intrinsic intrinsic nature of the curvature. So if a bug is living on that curve, it actually, by traveling through it, it can detect the curvature of the curve. Okay, so which means that as far as then the smaller circle, it will be able to determine that the smaller circle is not the same as larger circle. So say radius 1, radius 2. Okay, so it's, if it would be a person, you would just say you close your eyes. Well, okay, somebody is driving you at a constant speed, and you close your eyes, and you are and if you can detect how the car is leaning left or right, and you will know the shape of the curve roughly and the curvature. Okay, so and that is how you can detect the smaller circle from the larger circle, because in the smaller circle you will be leaning more steeply because of the curvature is higher. So, but we also established that the curvature of a helix is twice the curvature, or is the same as the circle of twice the radius. Okay, so the curvature of a helix of radius 1 is 2. Okay, so then the question is can you detect the difference between the curve between the helix of radius 1 and the circle of radius 2? They have exactly the same curve. Suppose there is no gravity to make reference to. Anyway, so that's something to think about. There are certainly also curvature issues with with surfaces, so that you can actually go on and examine these issues and think about the curvature of the surfaces, which we're getting to, and the curvature then on to our three-dimensional space and then four-dimensional space-time. All these issues certainly come up. Well, not in this class. But, yeah. Okay, so let's see. Okay, so we concentrate on surfaces, but not all surfaces, but only the surfaces that are graphs of functions of two variables. Okay, so that's roughly the beginning. So incidentally, how do you get out of it? How do you get the surface sphere? How do you get a sphere if it is not, if it fails the vertical line test? Well, the same problem, the same way we solve it here, from curves to parametric curves, from surfaces to parametric surfaces. Okay, so parametric surfaces will be another way to look at them, so that there will be no restriction of the vertical line test type. Okay, so surfaces given by graphs of functions of several variables. Okay, so the simplest example is we already have seen it, so I'm not going to do the review again. So it is z equal to f of xy. This is, so that's where dimension is equal to 2. Dimension of what? Dimension of the, let me do this again, parametric curves. So comes in a number, comes out a vector. Now we flip it. So functions of several variables. And then what comes in is a vector, comes out a number. Of course, every vector can be replaced, as we have done a few times, with a point. As long as it is a high-dimensional space, you could think in terms of points or vectors, depending on the circumstances. So if you do have the origin, then you have a vector OP, or you can concentrate on the point itself and nothing else. So that's the point P vector OP. Okay, either way. So we flip the whole thing. Instead of from numbers to vectors, we now going from vectors to numbers, and that certainly is not going to be very similar. Okay, so then the dimension that I'm talking about is then the dimension of the space. So Rn. So in this particular case, the dimension of the input space. So the difficulty, the complexity has been in the output space. Now the complexity, the output space, it's now in the input space. So dimension 2 is the two variables that are come in. And that is at some point we are now past the thinking about the function like this as a function of of two variables unrelated to each other. We could speak of something like this. Just like with parametric curves, we had what was it? P is equal to f of t. Okay, so f of t and p is actually could be a point or a vector. You can also express it as xy, but it is much more beneficial from the very beginning to try to incorporate as much as multidimensional geometry and vector algebra into this. So that's why this is better long term, just like this one. Also better long term, so that all the discussion that we had about parametric curves, with virtually no exception, is applicable to any dimension. But the examples will still be primarily low dimensional. So meaning 2. Okay, so once again, I want you to remind you about the two metaphors that I used for these two parts of the course. The first one is, the motion is always for parametric curves. The best way to imagine parametric curves is that the parameter is time, and then you have a location in space. Once again, that location could be either point or vector. It doesn't make any difference. So, and then the matching metaphor for the function with several variables is from location to, we're not going back to time, but rather, remember what the metaphor was? For each location, we associate what?
Height?
The height. Yeah, I like to say elevation to emphasize we're talking about the a map. Like a map of terrain. Okay, so, and then that, as we have discussed early in the class, you could have this composition. And that is the interaction that I talked about. This is the interaction between these two parts, but they do not rely on each other. So it just happens that if we want to do this composition, we actually have to know both of these. Okay, so we cannot get to this point and put some kind of composition here before we know both. Okay, so for example, if you want to speak of derivative of the composition of two functions, then you got to know the chain rule, but the chain rule not of that we have seen so far, but actually that incorporates this multidimensional situation on both of these functions. Okay, so we will. Okay, so that is number one. Now. As far as calculus is concerned, what is the calculus about? And you might remember that the way we started with, and in calculus 1 as well, you could speak of calculus in a number of ways. It is mathematics after all. So one of them is it is about change. And that is perfectly applicable to this part, to parametric curves. So the change in time, and then you change the time progresses, you change location, you want a rate of change, and you have derivative, velocity, acceleration, and so on. So this one is still applicable, but it's less less obvious, I suppose. So we're not going to use as much as analogy with motion, because once there is no time, look at it. That's the main metaphor, and there is no time there. So we have to speak of well, like this. So that's what I'm talking about. So say x, I'm looking from the side to my three-dimensional situation, and x is my location, the horizontal location, and the z is my elevation. Okay, so then that's what my graph might look like from a side. Okay, so then another way to describe, well, say it might be, actually practically speaking, it might be something curved, but what we actually concentrate on is tangency, and tangency and linear approximations. Well, to begin with, the calculus 1, it is a tangent line, right? So I have, let me just refresh your memory, y equal f of x, x equal a, tangent line. Well, how about let's start with the, if we're reviewing it anyway, I could actually do it with, start from scratch, and that is the secant line, right? So I'm looking at my curve, this is my a, this is, and then I make a step, a plus h, okay, and then I'm looking at, this is the point of my point of interest, but then I compare it to another point on the graph, which means simply that we have sampled our curve, and then we draw a secant line, okay? And that is a linear approximation. So the linear approximation is best way as we can if the function is still sampled before getting to actual derivative. So then the approximation is, okay, so let's write it out. So that's the linear approximation. Okay, so the linear, it is a line to begin with, a line through point A, f of A, f of A. Okay, so this is f of A. Okay, and that's one thing we need to know about the line. The second one is the slope. What's the slope? Rise over the run.
F of a plus h minus f of a over h.
That's right. Okay, so this is once again this h, and this is this is the numerator. That's the rise. Okay, and then so that's our best approximation if the function is simple. If we want infinite accuracy, we take h go to 0, and we have our derivative. Well, yeah, we take our derivative, so this will be f prime of a, and then my approximation becomes, well, let me write what happens beforehand. So if this is the case, my slope is this is my slope. I mean, this is the difference quotient. The slope that I wrote here is in fact the slope that we've done several times, every time, including yesterday when we did the difference quotient. So it's a difference quotient. Okay, so when we did Excel, that's what we did, and then we did not draw the whole line, but we did follow in the particular direction whenever necessary. So it will be, if this is m, let me write it out. It will be by point slope form. It will be y minus f of a is equal to m h. Hold on a second. Hold on, where's my x? yeah, it is actually H, but that is entirely convenient to write it this way. So let me put it X here. Okay, then X is equal to A plus H. Then I have my equation y minus f of A is equal to the slope times x minus A. Okay, so which is H. Okay, so that is my approximation of my function when the function is sampled. Now, if I go H go to 0, I will have my equation becomes y minus f of A. That part is the same, and but the slope instead of a difference quotient becomes the derivative, right? So this is something to comes from calculus 1. Also reviewed in calculus 2 when you did, remember, beyond linear, you did quadratic cubic approximations and Taylor polynomials as well. Okay, so we certainly will stick with linear approximations. This is what we have for functions of one variable, numerical functions. Now for parametric curves, the same story, but either you think of it as if we do this for every dimension, or which is better, you just look at the picture and just rewrite it vector-wise. So parametric curves, the same story. I have, what is it? So curve, and this is f of A, okay? And I have, what is it? Still the point slope form works. Well, actually, I'll give you the parametric parametric equation of the tangent line. So what's the parametric equation of the tangent line? Well, okay, so any, remember the parametric equation of any line. So we are moving from right to left, okay, which means that our tangent line also pointing to the right. What is the direction of the tangent line given by?
The slope.
No, I wouldn't put it this way.
The components of the...
It is simply the derivative. If that is the motion where we are pointing at every moment of time, the velocity, which is in other words to say, is simply the derivative. Okay, so the derivative is it is a vector at a particular point. It's a vector, and that vector gives me the tangent line through that particular point. Okay, so if we know the direction vector, remember? So we have a direction vector and we have a point. So that's number 2 item. Number 1 item is the point, which is f of A. Okay, so these two put together in the manner pretty much identical to this gives me the parametric curve, parametric representation of the straight line. So a straight line from this point in this direction. What's the equation? F of t equal
f of A plus t.
F of A plus, yeah.
Tf prime.
Tf prime, yes. Of A. Because this is a fixed vector. So we do it in one point at a time. Okay, so that's all there is. So this is, I guess, pretty much the core of the theory of parametric curves, or differential calculus of parametric curves. So where the tangent line is, which way it goes. Okay, so that is now we are switching from parametric curves now to functions of several variables. And I'd say it's really not that different, but we've got to develop it slowly. But it is going to be a surface. So once again, a point. Let's say it's P naught. Okay, then we have our x's are still here, x, y, z. So about the xy, the point P lies on the xy plane, so it's at some point AB maybe. Okay, the magnitude of all it is found. So this is This is where my value is. That's how we build the graph of the function. So it is AB, f of AB. This kind of computations create the graph of the function. So that's the graph of z equal f of xy. Notice the difference of the terminology. Calculus 1 graphs, this is also graphs, but in parametric curves, we have been speaking of paths. So this is a path. The difference is that where the thing lies. This thing lies in a larger space. So say if n is equal to 2, then the parametric curves lies on the plane. But when n is equal to 2, the functions of two variables, its graph lies in three-dimensional space. So the xy plane is the space of inputs, and z is the space of outputs. And it used to be exactly the opposite. Okay, the dimension 1 into dimension 1 for the output, it was for the input. Okay, so now the question is, what is the analogy? I think it came up not too long time ago. What is the analogy of a tangent line if we're talking about surfaces?
Tangent plane.
Tangent plane. So the analogy is tangent plane, which serves as what? It not only serves in this kind of informal way. It serves as an approximation, but also it serves as a linear approximation. In fact, the best linear approximation, just as was discussed in Calculus 2. A linear approximation, so in other words, a plane, it is a function of two variables once again. Just like our derivative over there was a substitute for our curve as far as long as we stay close to that point. Here also a similar situation happens. As long as we stay close to that point, there is a substitute for our curved surface, and that is the tangent plane. Okay, so linear approximation of f of xy, of z equal f of xy, around AB. Okay, so this was a linear approximation. This is a linear approximation for p is equal to f of t around t equal to a. Okay. Okay. So we're gonna pursue all of these, both of these ideas. So tangent plane. So it approximates the surface as best as possible, and if we zoom in, the surface looks like a straight line. And that is the idea. It's just like with the curve, whether it's parametric or not. If you zoom in on the curve, it looks almost like a straight line. We did it before. With surfaces, it's slightly more complicated, but you can certainly see this. So let me have it somewhere. This one maybe. I'll go with this one. Why not? Okay, so that is our surface. Okay, so given by it is the graph of function of two variables. But if I zoom in on this point, which is where x and y are equal to 0, so then how? I will just make h smaller. Okay, so it's really curved, but if I make the step to the left in these two directions this time, it just happens to be the same step. If I make it smaller, it will start with a straight line. So, for example, if I put 0.5 here, okay. So as you can see, that's literally what's happening. We're zooming in, and the area around the corner becomes flatter and flatter. It was kind of flatter to begin with, but if I put here 2. Is almost, as you can see, it's colored the same color, blue color, which means that there is virtually no change in the elevation. And then I could, maybe one more. If I put 05 here. Well, as you can see, to appreciate how flat it is, you look over here. As you can see, the elevation is very, very minimal. So the Excel continues to rescale the whole thing, and that's why it still captures the change. There is some change, but it gets flatter and flatter and flatter, and you can see that the change, it looks almost the same as it was in the beginning, but you can see how the numbers have decreased on the z-axis, and therefore the elevation is virtually non-existent. So that is how we zoom in on the surfaces, and once again to realize that you have tangent planes. Well, let me do some really small number here. I have a couple of zeros here. Well, so as you can see, there is virtually no elevation. Or look at how many zeros over there. But Excel still very carefully looks at even very tiny changes it detects. Okay, so tangent planes. Why do we look at tangent planes? Well, same reason why we looked at tangent lines in Calculus 1. So, like examples, do you remember examples from Calculus 1? Tangent lines in real life, other than motion. A curve, and then the tangent line has some meaning or importance.
It's the best linear approximation.
Well, that's mathematics. I thought anything that you can have practical. One example would be, say, optics, and you have a curved mirror or a curved lens, and to find out how the light will bounce off it, you need to know the tangent line. Just about almost literally, you need the tangent line to know where things are going to go. So if this is the lens, and this is the light approaching it, so which way is going to go once it hits it? Well, you find the tangent line through this particular point, and then remember how it works out. The same angle. This is the same angle, but you don't know where that angle to choose with respect to what you measure that angle if you do not find the tangent line. So the idea is that it's as if that single particle or photon or whatever, it almost bounces off the curve as if it is a straight line. But what straight line? It is the tangent line. Okay, so that's one way. Either, like I said, it's a mirror or any kind of lens, and it is curved, and by design it's curved, so how do you know where it goes? That's how you find the tangent line. Okay, so this is, you can certainly make that argument, that tell that story in Calculus 1, but really if you progress to, it would be an incomplete story, because most of the time the curves are, the lenses or mirrors are not one-dimensional, they're two-dimensional, they're surfaces typically. Okay, so say if you have a spherical object, you want to know which way the light is going to bounce. In fact, that story, remember the story about Archimedes and how he defended his city of Syracuse against the Roman invasion? With the story is he set the ships of Romans on fire with apparently shields like this, the red shields of some soldiers in a particular way, so that they would bounce the sun, lights of sun, towards one particular location. Okay, and that's where the ships were, and then presumably they may have set them on fire according to the story. Okay, so what was the shape of the curve?
Parabola.
It was the, who said it?
Parabola.
Okay, well, why is that?
Because whenever it bounces off, it goes to its direct point.
Right, if the lights come into, no matter which way, from which direction the light come, they all end up at the focus of the parabola. Which, you study parabolas, quadratic curves, but where the focus is located, it never really comes up. But there is that special point in there, and so once again, wherever lights, no matter how, in what direction lights come in, they all end up at the same location. How do we know? Technically you need the tangent lines to establish that. And once again, it's really not a curve then, but it is a surface, and so it's not a parabola, but a paraboloid. You take a parabola and rotate it. Okay, and that how you have the surface with the same property. So it will bounce all the lights at the focus of that parabola. Okay, so once again, a parabola, and you rotate it, and you have a parabola. Headlights going the other way, because it has a one going the other way. The lights go the other way. You have a light source here. It sends it back to a parabolic mirror, and it reflects parallel lines. Parallel lines. Okay, so which is what you want from a headlight. Okay, so that's an idea that is being used. Okay, so and then any kind of bouncing thing, object bouncing off a curved surface. It applies doesn't have to apply to light or anything like that. Actually, there's also, you may have heard of this what it's called, this time it's the elliptical room, a room of whispers, I think. Anybody heard of it?
Oh, where you can stand on one side and whisper.
That's right. So there are two foci. If you stand in one focus, no matter how far, the sound bounces off back to the other person, or you can listen even if you're having between some objects or people, doesn't matter, because the sound bounces off the walls and comes to you. Okay, so all of this applies, but ideally you deal with not with curves, but rather with surfaces. And you're just lucky that in this particular case you can just you rotate the paraboloid and you get what you want. But sometimes you start with the surface and you're studying its properties. Okay, so it could be, remember that story in LA, as well as in Las Vegas, as well as in London, the curved skyscrapers they've been building recently, and they reflect light, and sometimes on the sidewalk. In Las Vegas, people complain about sunburns. In LA, also something was melted. The Opera House, I think, in LA, they had that problem, and in London, I don't remember what that was. So that's all what titaniums are about. And once again, it has nothing to do with motion. So it has nothing to do with parametric curves. And calculus 1 is really not enough. Okay, so we have to understand the surfaces and how to approximate them with their tangent planes. But first, then let's understand what a plane is, and we want to have an equation as simple as this, just for a plane. For a curvature, for a straight line, the parametric equation of the straight line is simple. It is P naught plus T V. Okay, so that is a general curve, a general parametric representation of a straight line in the direction of V from passing through point P naught. Okay, so we want to have something similar, and but this time we wanted to speak of planes. So the equation of the plane is what we want, and we want to answer the question in a manner very similar to this, meaning that one. So a point and a vector is sufficient to define a line, and in this particular case, what we're going to do is slightly different. Okay, so we'll find new representations of planes. This time as functions of two or more variables. We'll start with two. Well, the equation is actually quite simple. Z is equal to A plus bx plus c1. So in other words, it's an arbitrary linear function. A linear function, so as you can see, the two variables, x and y, and the dependence of z on x is linear and on y is linear, and that gives you the general linear function. Okay, so if we just start trying to figure out the meaning of these three coefficients, just like we had, you remember, y equal mx plus b, and we were able to figure out that b is the y-intercept and m is the slope. Something similar is going to happen again. Okay, so what is the meaning of A?
A is the point?
No, you see the trouble with, we are living in three-dimensional space, so every point will have three coordinates. Okay, so if anything, A is similar to B. It is instead of y-intercept, what is it?
It's the z-intercept.
It is the z-intercept. In other words, that's where the plane crosses the z-axis. Okay. Okay, and then it's really not hard to figure out what is that we're looking at with B and C. I will just concentrate entirely on these two separate planes, this one and that one. So I start with saying let y equals 0. So in other words, I'm looking at the intersection of my plane with this vertical plane. Okay, so if y is equal to 0, then what I have is z is equal to a plus bx, which means that you can tell me now what b is.
It's the y-intercept?
No, it's a slope with respect to x. So if we are concentrating on this plane, xy plane, then b is the slope of my line. Slope over x, and then if I set x equals 0, then I have z is equal to a plus cx, and then c is slope over y. Okay, so we'll just continue this next time. There's work to be done.